The title of our paper is Facial Landmarks-Based Region-Level Data Augmentation for Gaze Estimation. Human gaze plays an important role in identifying the user's point of interest in terms of the direction, location, attention, emotions, and interactions. Generally, human gaze estimation is a frequently used approach to gain a better understanding of human cognition and behavior. Many studies have addressed the approaches to trace the position and the direction of eye gaze, which is required for different domains like cognitive, social behavior, medical health, commercial, and other human-computer interaction applications. Human gaze estimation methods fall into two broad categories: model-based methods and papyrus-based methods. The model-based method require dedicated devices such as near-infrared cameras to manually regress the eye features and build a geometric model. This method is person-specific and restricted to constrained environments. In comparison, a papyrus-based method don't need dedicated devices and are not limited to constrained environments. Some papyrus-based methods using CNN have been proposed and show convincing results. This also benefits from the powerful feature extraction capability of the CNN. With further research on gaze estimation, it is found that face images contain rich, useful information. Data augmentation has been proved to be an essential technique for increasing the effective data size and promoting the diversity of training examples. We can use data augmentation to augment facial information. Subtle changes in eye regions are important for the gaze estimation. However, direct data augmentation on faces is likely to damage key features in the eye region. Besides, data augmentation methods such as flipping and affine transformation can reduce the performance of gaze estimation. Because these methods change the implicit features of face images, we have the following three motivations. The first one, data augmentation is an effective technique and is widely used in various deep learning tasks. The second one is that subtle changes in eye regions are important for gaze estimation. So, direct data augmentation on faces is likely to damage key features in eye regions. The last one is that non-eye regions also contain rich information that can contribute to gaze estimation, such as hand pose, illumination. So, we propose a facial landmarks-based region-level data augmentation method for gaze estimation. Our method has two steps. Firstly, as shown in the green box, we use landmarks to divide the face image into eye regions and non-eye regions. Secondly, as shown in the red box, we generate face images under different data augmentation methods by augmenting non-eye regions. We fuse the augmented non-eye regions with eye regions to generate the final augmented image. In this way, we can ensure the key features of eye regions are not affected and enrich the features of non-eye regions. We firstly use landmarks to get a face image with 68-point calibration, and we connect the number 1 to number 17 calibration points in turn to draw the face counter. We divide the face image into the eye region and non-eye regions using these calibration points. The red box shows that the augmentation process of the non-eye region. We generate non-eye regions under elimination conditions, random occlusion, and Gaussian blur. Due to the changes in elimination conditions, the same face appears differently. So, we adjust the brightness, contrast, and saturation in order to generate different elimination conditions. We use random erasure and Gaussian blur to reduce the impact of gaze irrelevant features such as occlusion and texture on the training model. Illumination is one of the important factors that affect the facial features. Due to the changes in illumination conditions, the same face appears differently. In our process of illumination synthesis, we generate face images by adjust the brightness, contrast, and saturation. We compare images augmented directly on the face and images augmented with our method. The first row shows original face images, and the second row shows images augmented directly on the face. The third row shows images augmented with the proposed method. If we augment the face image directly, it is likely to damage the key features of iris. For example, the iris may be erased. Our data augmentation method only works on the non-iris, and the key features of the iris are fully preserved. In the part of experiments, we have three input branches: eye image, face image, and face grid. We only use ResNet as our training model for gaze estimation without any other structures. Finally, all branches are connected through fully connected layers to output the gaze point or gaze directions. The experiments are implemented using PyTorch. We only use the ResNet as the training model. Network parameters are initialized by the default initialization of the PyTorch. The model is trained for 18 epochs on the gaze capture, and the batch size is set to 32. The initial learning rate is set to 0.001, and it becomes 0.0001 after 8 epochs. The optimizer uses SJD, and further we use a momentum of 0.9 and a weight decay of 0.0005 throughout the training procedure. Gaze capture is the largest 2D gaze dataset with more than 2 million images from more than 1,400 subjects. The dataset is captured by mobile phones or tablets in different orientations. There are more than 1,400,000 frames have both face and eye detections, which are further divided into training, validation, and test images. For training, each of the samples is treated independently. For testing, we average the predictions of the samples to obtain the prediction on the original test samples. We conduct two experiments test different methods on the gaze capture dataset. We choose four methods for comparison on gaze capture, which are iTracker, SAGE, TAT, and AFFnet. The results are shown in the table. To the best of our knowledge, AFFnet shows the total performance on the gaze capture. Our proposed method achieves 1.58 cm error on mobile phones and 2.36 cm error on tablets, which outperforms the methods on mobile phones. For the mobile phone image test, the iTracker has the highest error as 1.86 cm. SAGE and TAT has similar performance around 1.77 cm, improve about 5% from the iTracker. AFFnet achieves 1.62 cm error, which outperforms both two methods significantly. Our proposed method achieves 1.58 cm that outperforms AFFnet and improves about 15% from iTracker. For the more challenging tablet image test, the error of iTracker is 2.81 cm. SAGE and TAT has similar performance around 2.69 cm. AFFnet achieves 2.3 cm error, which is almost 0.39 cm lower than the SAGE and TAT. Our proposed method achieves similar results to AFFnet, and the error is 2.36 cm, which is about 12% lower than SAGE and TAT. The proposed method can improve the performance of gaze estimation on tablets than most previous methods. This experiment results show that the proposed method has clear advantages over other methods, especially on the mobile phone devices. For the more challenging tablet test, the error of the proposed method is 2.36 cm, which is about 2% higher than the AFF net. The reason is that the tablet image is less than the phone image in the dataset. The proposed method has great room for improvement on the tablet devices. In this section, we design experiments to demonstrate the effectiveness of the proposed method. Firstly, we test the error of the model without using any data augmentation methods. Then, we directly augment faces and test the error. We compare these two results with the result obtained by training with our proposed method. The results are shown in the table. Without data augmentation, the error of mobile phones and tablets is 1.68 cm and 2.59 cm. Data augmentation methods on full fish reduce the performance of the model. The error on mobile phone and tablet is 1.73 cm and 2.82 cm, which increased by 0.05 cm and 0.23 cm. Because data augmentation methods applied directly on full fish reduce the availability of key features in irisons. For example, the irison may be completely erased. With no irisons data augmentation method, the error of mobile phone and tablet is 1.58 cm and 2.36 cm. The error is reduced by 6% and 9% for mobile phones and tablets. We can know that directly augment full face can increase the error of the model. With no irison data augmentation, the error is reduced. Finally, we summarize our research work. Firstly, we propose a facial landmarks-based region-level data augmentation method for gaze estimation. The faces are divided into irisons and no-irisons, and then we generate face images under different data augmentation methods by augmenting no-irisons. Secondly, our proposed method achieves good performance on the gaze capture dataset, which is the largest 2D gaze dataset. On tablets, the proposed method is close to the current sorter methods, and on mobile phone devices, our method outperforms the sorter methods. The results prove the effectiveness of the proposed method. And the last one is gaze adaptation and its applications are promising research topics. We hope researchers will be inspired from our work. Our work is not complicated. On the contrary, our work is straightforward and easy to understand. More importantly, our work is effective. By adjusting the reason of action of the data augmentation method on the fish, we can achieve sorter in the largest 2D gaze dataset using only the common ResNet model without any other structures. We believe that any computer vision researchers can rebuild our work after reading our paper. Okay, thanks for your watching. If you have any question, you can contact me with the email in our paper. I will try my best to give you a detailed answer as soon as possible. Thank you.